Hey everybody, this is the video for two sections, 11.5, which is on the alternating series in general, including a test for convergence of an alternating series and an error estimate for the alternating series. And then there's also the ratio test. 11.6 includes the root test and the ratio test, and we have chosen to exclude the root test from this semester's curriculum. Okay, so to start off with, I'll tell you when we switch into 11.6 land, but this is 11.5 alternating series. So what is an alternating series? Well, you start off with a base sequence a sub n, and we're going to insist that this sequence has all positive values. So a sub n is greater than 0 for all n. Then, if you have this base sequence, you're going to flip-flop it with a -1 on the even terms in your series. So you're taking your positive sequence, but every other term is going to be negative. And what that ends up looking like is if you're adding these numbers up, well, if you start at 0 and you add a sub 1 to 0, you, of course, end up out here at the x value a sub 1. That's also the value of your first partial sum. Then, from a sub 1, if you add a negative a sub 2, so when n is 1, let me just say this. When n is 1, your sum term is just a sub 1. When n is 2, that second term in your series is a minus a sub 2. And if you add the opposite of a sub 2, that's a negative number, and you end up over here. So that is a sub 1 minus a sub 2, which is the second partial sum. And then if you add -1 to the 3 minus 1 times that sequence term a3, well, that's -1 squared times a3. So a3 sign does not get changed like a2 sign did. So you're going to add a positive a sub 3, and from where you were in the sum, that lands you over here. So this is now a1 minus a2 plus the positive value of a3. There's your s sub 3, your third partial sum. Similarly, from that point, if you then add your next term in the series, that is -1 cubed times your fourth sequence term, and that's a negative a4. So you're adding a negative a4 to the previous three terms. That's going to land you over here. So there's your fourth partial sum. And just to finish the example, when n is 5, you have -1 to the 5 minus 1 times your fifth sequence term, and that's -1 to the fourth times a5, which is a positive a5. So you're adding a positive a5 to the fourth partial sum to get to here. That ends you at s5. So if your partial sums are going to converge to something, if this alternating series is going to converge to something, you definitely need for these terms in your sequence to be going to 0. And you can see that. So, of course, that is required for any series to converge, but you can really see that in this alternating series picture. Okay, so given an alternating series, we can tell if an alternating series converges if, first of all, you need all of your terms, every single consecutive pair of terms in your sequence to be decreasing, okay? So a sub n plus 1 is the term that comes after a sub n, and we need this to be smaller, okay? And then we need them to be getting smaller and smaller, but we also need them to be approaching 0, okay? And if both of those are satisfied, then the alternating series will converge to a finite value. So here's some examples of alternating series and also applications of the alternating series test. So first example that we're going to check out, this actually came up on your 11.2 worksheet, those exercises at the very end. So I'll just say this is the 11.2 worksheet. Last page, bottom of the last page are the exercises, and this was like 1C on the exercises at the bottom. Okay, so 11.2 was an introduction to series and specifically looking at geometric series. So what we actually showed in that worksheet was that this series can be written as negative 1/3 raised to the n minus first power. And written in this form, you can see that this is a geometric series with a value 1 and common ratio x equaling negative 1/3. Well, because it's a geometric series, you can use the geometric series test for convergence. Because the common ratio's magnitude is less than 1, this series converges. And you can even tell what it converges to, but we're not so oh man, that word just is evading me right now. Concerned. We're not so concerned with what it converges to. We just want to know if it converges. But here is how you can see that this same series is not just geometric, it's also an alternating series. So by pulling the negative sign out of the negative 1/3 to the n minus 1 power, you can see that this is now an alternating series. And if it's an alternating series, you're going to be asked to verify that it is an alternating series by just telling us what the positive terms in the alternating series is. So you can see in an alternating series, you have the negative 1 to the n minus 1, and then you have these sequence terms a sub n. So our a sub n terms is the part of the series that is not the negative 1 to the n minus 1. So our a sub n is 1/3, positive 1/3 to the n minus 1. And what makes this an alternating series is that you have the minus 1 going back and forth times a positive sequence. So this is a positive sequence for all n. So because it's an alternating series, we can actually apply the alternating series test that is this theorem above. The first thing we need to check is that this series is decreasing. Well, our n plus first term is 1/3 to the n, and our nth term is 1/3 to the n minus 1. Well, this inequality is definitely true because the denominators of these fractions have this relationship. So of course, if this relationship is true, then the inverse of that inequality will be true when you reciprocate those fractions. Great. Okay, so that's the first part of the alternating series test. That doesn't guarantee that it converges. The last thing that you need to check is that the limit as n goes to infinity of your sequence, your base sequence, without the negative part, does in fact converge to 0. And this one does. Okay, so both properties that are required to apply the alternating series test hold, therefore this series converges. So you can see this series is both geometric and alternating. You can use either test to determine that it converges, but maybe on a test or a quiz, you might be asked to use one specifically. So make sure that you can do both. Okay, let's look at another example. I need this to be smaller. Okay, another example. How about the series from n equals 1 to infinity of minus 1 to the n minus 1 all over arctan of n. So first of all, this is not a geometric series in contrast to example A. So this is not a geometric series, so we can't use the geometric series test of the common ratio to determine convergence. It is, however, an alternating series. And again, if you claim something is an alternating series, you better explain why. And the reason is the terms that do not include the negative 1 to the n minus 1 are of the form 1 over arctan of n. Okay, so here is that a sub n term, 1 over arctan of n, and you can see that the negative 1 to the n minus 1 is left out of that. Okay, so that is always bigger than or equal to 0 for all n, because our n values are positive, right? We're plugging in 1, 2, 3, and 4. Okay, so it's an alternating series. And that means that we can apply the alternating series test. So the first thing we have to check is that we are decreasing. So we need to check that the n plus first term is always smaller than its previous term. That is equivalent to asking that 1 over arctan of n plus 1, that is the n plus first term of our sequence, we're asking that that be less than arctan of n. And I shouldn't have put this inequality here until we verified that that was true, but it is true. And so it's true because we're going to play the comparison of the denominators trick a lot. So hopefully you feel okay about, comparing denominators as a way to compare two fractions. Okay, so because arctan is an increasing function, arctan of n plus 1 is going to be larger than arctan of n. Okay, so that condition for the alternating series test checks out. Let's check the second part. We cannot apply the alternating series test unless both of these conditions are verified. So the second condition is checking if our base sequence, a sub n, converges to 0. And our base sequence is 1 over arctan of n. Now, if you remember what the graph of arctan of n looks like, it actually has a horizontal asymptote. And this is going to go to 1 over the value of that horizontal asymptote, which is pi over 2. So in fact, this limit converges to 2 over pi. That is not 0. So because this is not 0, this series cannot converge. Okay, so by the alternating series test, this diverges. All right. Okay, great. So if we are able to determine when a series converges, say this one, how would we be able to compute its value? With a geometric series, we had a really nice way of actually not only determining whether or not a series converged or diverged, but also actually determining its value if it converges. So I'll just say that actually computing the value of an alternating series is not going to be simple, and we're rarely going to ask you to do something like that, if ever, in this course. So actually computing the value S of an alternating series is very hard. The best we're going to do is estimate. And this might kind of feel similar to some of the estimations that you did in, what was that section? Like section 7.8, where we talked about the error bounds in the midpoint trapezoid and Simpson's rules for approximating an integral or approximating an area. Okay, so if you have an alternating series and you know that it converges, in other words, it satisfied properties 1 and 2, properties 1 and 2 of the alternating series test, then this value S that it converges to, it's hard to find, but we can approximate it using the partial sums, S sub n, within some degree of accuracy. How accurate? Well, within the a sub n plus first term. So that might seem kind of odd, but let's do an example where we can see this worked out. Okay, so first off, I just want us to verify that this is an alternating series. Why is it an alternating series? Well, it has the -1 to the n minus first power. That's great. It is an alternating series, but we need to verify that the base sequence that's being multiplied by positive or -1 is always positive. And our base sequence is 1 over n, positive 1 over n. And that is always greater than or equal to 0. So again, here is that base sequence, 1 over n, where we're excluding the alternating part. Okay, so this is an alternating series, which means to test for convergence, let's use the alternating series test. The first thing that we'll check is that the sequence, the base sequence, is decreasing. Well, a sub n plus 1 is 1 over n plus 1, and a sub n is 1 over n. And as a matter of fact, 1 over n plus 1 is less than or equal to 1 over n because n plus 1, the denominator, is greater than or equal to the other denominator. There's that denominator reciprocal trick. Okay, so that is verified. Now let's check the second condition that we need to verify. Is the limit as n goes to infinity of our base sequence 0? Yep. Great. So both conditions are satisfied. That means the alternating series tells us that the series -1 to the n minus 1 all over n converges. All right. Now that we know it converges, we know it converges to some value s. Okay, that's what we keep calling s, the convergent value. So to estimate this value s within a certain level, within a certain error bound, here's what we're going to do. The first thing that we need to do is we need to find n so that our actual value s and our estimated value s sub n is less than 0.1. Well, we know that s minus s sub n is less than the magnitude of our n plus first sequence term. And our n plus first sequence term is 1 over n plus 1. So it suffices to find n so that 1 over n plus 1 is smaller than the error that you want. Well, n plus 1 is less than 0.1 so long as n is bigger than or equal to 10. And you can actually solve that inequality just by cross multiplying if you'd like. Okay. Actually, we can make that 1 smaller, can't we? We can make this bigger than or equal to 9. Okay, great. So, the second thing that we need to do now that we have this n value is we need to actually compute s sub 9, the ninth partial sum. So s sub 9, using the definition of our series, is -1 to the 1 minus 1 all over 1 plus -1 to the 2 minus 1 all over 2 plus -1 to the 3 minus 1 all over 3. I'm going to ignore some of those instead of writing them all out. Okay, so those are the first 9 terms in our series. The first one reduces to 1, the second one reduces to negative 1/2, the third one reduces to positive 1/3, and here are the terms that I did not write out above. And then we've got a negative 1/8 plus positive 1/9. Okay, so this is equal to, hopefully I did this right, because I actually did n equals 10 in my solutions, but this is equal to then 0.74563492063. Okay, so those fractions add up to exactly that decimal, and that decimal is within 0.1 of the actual value of that series convergent value. Okay, so that's how you apply the alternating series estimation to get some value that's close enough to the actual value of that series. Okie doke. So series are kind of interesting. We're talking right now about series whose terms bounce back and forth from positive to negative values, positive, negative, positive, negative. We could look at a series whose terms are just a mixture. They don't go back and forth in that pattern, but we have some positive and some negative. We could have series whose terms are all positive or are all negative. So every single series, regardless, so I just want to underline this, every single series where a sub n could be positive or negative can be broken into these categories. A series could be what's called absolutely convergent, and you're absolutely convergent if you converge and the series, this other series that is adding up the magnitude of all of your sequence terms also converges. And I just want to say that when you take the magnitude of stuff, that makes everything build up faster, which is making it less likely that something would converge. So just because your series converges does not mean that the series involving the magnitude of your sequence will converge. Then there's another category where you are conditionally convergent, and that is where your original series does converge, but when you take that magnitude, it doesn't converge, it diverges. Okay, maybe the third category is where your sum diverges. And by the way, if this diverges, the magnitude definitely diverges. Okay, so just for a little Venn diagram so you can see this, you have series converging, you have series diverging, and of course these should not intersect. And then within a series converging, you have series whose magnitude sequences have a convergent series. Okay, so in here, that would be somebody who is absolutely convergent. If you fall inside the larger circle but not within the smaller one, you would be conditionally convergent. And if you just simply diverge, you'd be over here. So that just hopefully helps you see how these definitions relate to each other. Okay, let's get on with it. So the first example, we are asked to determine if this series converges absolutely. That would be the best possible scenario. That would be an orange category. We are asked then if it doesn't, does it converge conditionally? That would be in the yellow category. And then we'll justify those answers. And if you converge, so if you're yellow or orange, find the partial sum so that you are within 0.2 of the exact value of that series. Remember, the exact value is hard to find, but we can go, as long as it's an alternating series, we can approximate the actual value to some degree of accuracy. Okay, as always, I'm going to verify that this is an alternating series. This is an alternating series with base sequence, the part that does not have the -1 attached, 1 over n squared. Those are always positive. Okay, and that verifies that you have an alternating series with the -1 to the n-1 attached. Okay, so because it's an alternating series, we can use the alternating series test to determine if our series is at least in the yellow category, okay? So the first thing would be, does your series have sequence terms which decrease? Well, this would be true if the n plus first term in your sequence is bigger than or equal to, nope, I lied to you. It's backwards. You want your terms to get smaller as you move forward. So is this less than or equal to its previous term? And this is true because, of course, n plus 1 quantity squared is bigger than or equal to n squared for all n. So that checks out. I'm going to give it a blue check mark. So that first condition of the alternating series test is confirmed. The second one we need to check is that the limit as n goes to infinity of your base sequence is 0. Yep, that works too. Okay, so by the alternating series test then, because both of those have blue check marks, your original series converges. Now, that means that you are in the yellow category. You could be in the orange category. So let's see if you're in the orange category. So that would mean that the sum from n equals 1 to infinity of the absolute value of your old series terms converges. Well, what's the absolute value of those terms? Well, -1 to the n-1 in absolute value is always 1, and n squared is always positive. So that's the new series that we're considering. And by the p-test, remember the p-test from 11.3, 11.4, that converges. Okay, because p is 2, and that's strictly greater than 1. Okay, so in fact, this series, this original series, is not just convergent, it is absolutely convergent. Okay, so let's say that. Our original series is absolutely convergent. That's the best possible scenario. Great. Okay, so the last thing that we are asked to do, and I know we're running out of space here, but we're asked to estimate. So the estimate that we need to do is we need to first find an n value. Remember how we did this up here? Find an n value so that the difference between the actual value and the s sub n partial sum is less than the degree of accuracy you want, or the amount of error that you want. So we want our error bound from our theorem, a sub n plus 1, to be smaller than 0.2. Well, a sub n plus 1 is 1 over n plus 1. Okay, and we need that to be less than 0.2. Well, that means that we want 5 to be less than n plus 1 squared. And that is true if root 5 minus 1 is less than n. Okay, so n being greater than or equal to 2 will actually give you an estimate that is within 2/10 of the actual value. So I'm not going to do that, but your answer then would be compute s sub 2. That value of computing s sub 2 will be within 0.2 of the actual value of this original series. Okay, let's do that again. So we have another series. It's an alternating series. What's its base sequence? What is the part of it that is not negative? That would be 1 over n. And that's always bigger than or equal to 0, regardless of n. So that verifies that it's an alternating series. So we can use the alternating series test. I'm going to abbreviate that by AST. The first thing that we verify is that this is a decreasing sequence. And a sub n plus 1 is 1 over n plus 1. A sub n is 1 over n. And the inequality here is, in fact, what we want it to be. And we need to explain why. That's because the denominator n plus 1 is bigger than or equal to the denominator n for all n. Great. So that condition of the alternating series test checks out. The second thing we need to check is that the limit as n goes to infinity of our base sequence is 0. It is. Great. So that means that the alternating series test applies and our series converges. Okay. So our series converges, which means, excuse me, it's at least in the yellow category, but it could be in the orange category. It could be absolutely convergent. Okay, so to determine if it is absolutely convergent, we need to take the absolute value of all of our terms and add those up. Well, the absolute value of all of our terms is 1 over n. But we know that this series, the harmonic series, which you saw in, I think, a couple previous videos, the harmonic series diverges. And this is true by the p-test, or by the p-series test, because the power of n is 1. Okay, so this diverges, and that means that it is not absolutely convergent. This means that the original series from n equals 1 to infinity of negative 1 to the n minus 1 all over n, it's not absolutely convergent, it's only conditionally convergent. Okay. Great. Okay, it's conditionally convergent. Okay, so the solution for the approximation is already on Canvas. So I'm gonna let you look at those solutions. Okay, last problem. Okay, so this guy is an alternating series. Let's just verify what the positive part of the series terms are. They are 1 over 6 to the n times n factorial. Now here's an interesting thought that I want to point out. Notice that in this series, you have negative 1 to the n, not negative 1 to the n minus 1. The way to fix that, I'll kind of do fix that in quotation marks, even though you can't see my face. N minus 1 times negative 1 to the 1. The bases of negative 1 will recombine so that their exponents add back up to n. But you can bring this negative 1 to the front, okay? Once you move that negative 1 to the front, you're essentially dealing with an alternating series that is exactly of the form that we've been looking at with negative 1 to the n minus 1. So we don't really need to do that. This is still an alternating series, but it has a negative 1 that flips which terms are negative and which ones are positive. Okay, so our a sub n terms are bigger than or equal to 0 for all n. Okay, and that means that this is an alternating series. We can check that our terms are decreasing. The n plus first term is 6 to the n plus 1 times n plus 1 factorial. and we would like to compare that to the previous term in the sequence, which is 6 to the n times n factorial. Okay, oops, these should be in the denominators of some fractions there. Okay, so this inequality that we want to be true is in fact true, but let's explain why. This is true. First of all, we want to say because the denominator of the left-hand side is larger than the denominator of the right-hand side. Well, why is that true? Just so we can be really specific. Because 6 to the n plus 1 is bigger than 6 to the n, okay? And n plus 1 factorial is bigger than n factorial. Okay, so basically you have the product of two things, both of which are larger than these two things, so the products must respect that inequality. Okay, so that property of the alternating series test works. The last check is that the limit of our base sequence 1 over 6 to the n times n factorial is 0. Yeah, this denominator, 6 to the n times n factorial, that is getting really, really large really fast, and you've got a fixed value in the numerator, so that is 0. So the alternating series test, again, applies, and it says that this series converges. Okay, great. So I think I will also have you go ahead and read the error estimate solution. Okay. All right, so we are, whoa. Sometimes the stuff that's actually behind the writing just vanishes. It's pretty weird. It's pretty spooky. Okay, so that concludes our 11.5 investigation. Just in a summary, we've introduced what an alternating series is. We have discussed when an alternating series converges or diverges. However, knowing if something converges or diverges does not tell you what its value is, right? If it converges, then the best you can probably do is estimate it. And you can estimate it within whatever amount of error you want. If you want a very small amount of error, you can find the nth partial sum that gives you that is within that amount of error to the actual value. Then we said that any series at all, can be clumped into two categories. It either converges or diverges. Any series will converge or diverge. If you take the absolute value of the terms in the series and you look at this series instead, if that new series converges, then your original series is what's called absolutely convergent. If your original series converges, but when you look at this new series, it diverges, then your original series is what's called conditionally convergent. Okay, great. Okay, oops, which means, sorry, we didn't even check this one. I'm just going to tell you, this one is absolutely convergent. So you need to check that this series converges, because that is the series whose terms are the absolute value of the originals. Okay, that is absolutely convergent. Great. Okay, so now we are in 11.6 land, and as I said before, 11.6 discusses both the root and ratio tests. Due to time and also just general usefulness, we are going to not do ratio or root test. We're only going to do ratio test, which means on WebAssign, we've eliminated the exercises that are on the root test. So you should only see exercises that are on the ratio test. If you come across a problem that's on the root test, you should email myself or Dr. Hamidi to let us know that there's a problem there that shouldn't be. Okay, so the ratio tests. just so you can, I know these videos are sandwiched, but the ratio test applies to any series, not just alternating series. We're kind of coming back out of the alternating series section. So let's go ahead and apply the root test to these series. So maybe the first thing that you would want to do before, of course, when you're out in the wild and you encounter a series, you're not going to be necessarily told what convergence test to use. So it would be a good idea for you to pause, see if there are any special attributes of the series that you're looking at. For example, is this an alternating series? It is, which means you could use the alternating series test. The ratio test might also apply, except in the case where it is inconclusive. So we will actually hit A, B, and C through these examples. They actually correspond exactly to the parts of the theorem. So we'll go into the details once we apply the limit test and try to get the result from that. Okay, so ratio test means you're going to compare the ratio of the terms in the sequence as you go to the next one. So if my sequence is 1, 2, 3, 4, 5, 6, 7, 8, then there's always some sort of a pattern there, n plus 1, n plus 2. So I would be comparing n plus 1 to n. Those two terms are consecutive, and I'm comparing the ratio that they form. So the idea here is if this ratio is less than 1, then that tells you that, generally speaking, the sequence is getting smaller because the numerator of this ratio would then be smaller than the denominator of this ratio eventually. Okay, so for our series here, our terms are a sub n plus 1 is negative 1 to the n plus 1 times n plus 1 squared all over n plus 1 factorial. So that is a sub n. And instead of that's a sub n plus 1. And instead of writing a sub n underneath it, I'm going to write its reciprocal because we're dividing by it. So the reciprocal of a sub n would be n factorial divided by minus 1 to the n times n squared. So just to be clear, what I've written here is a sub n plus 1, and what I've written here is 1 over a sub n, because their product gives us the ratio that we're trying to compute. Okay, so whenever you do the ratio test, if your series is alternating, those negative ones to a power, those are going to disappear. And everything that's left is typically then positive. So here's what's left over. That's what's left over from a sub n plus 1. Here's what's left over from a sub 1 over a sub n. And now that you have those negative numbers all canceled, and you're comparing now these two, or you're trying to take the product of these two fractions, some cancellation will happen. So here's something that you need to be very comfortable with. N factorial and n plus 1 factorial, let's do this on the side. So n factorial and n plus 1 factorial, if we write out a couple terms, n factorial is n times n minus 1 times n minus 2 times n minus 3, so on and so forth, times 2 times 1. Okay, so you just march all the way down the line, starting at the positive integer n, all the way down to 1. Similarly, n plus 1 factorial is n plus 1 times n minus 1 times n minus 2 times n minus 3, march down the line, times 2 times 1. So anytime you have factorials in both the numerator and the denominator of the same term, both of these are n's, you're going to get massive cancellation. So everything in the smaller terms factorial is actually contained in the larger terms factorial. So those will reduce to be n plus 1 squared. N factorial is gone because it is contained inside of n plus 1 factorial, and the only thing that is then left in the denominator is n plus 1 times n squared. Okay, so we could do further cancellation. N squared over n plus 1 cancels, and we are left with n plus 1 over n squared. So what we want to do now is we want to take the limit as n goes to infinity of this ratio that we just computed, and we reduced it so that it would be easier to take the limit. So we are looking at the limit as n goes to infinity of n plus 1 over n squared. And while n and n squared both go to infinity, n squared goes to infinity faster. So this is 0, which is less than 1. So by part A of the ratio test, this means that this series converges. Okay, great. Let's do the next one. So again, first thing you might want to ask yourself is the series I'm looking at a specific type of series? What you've seen so far in terms of nice series are geometric series, 1 over n to the p series, and alternating series. Those are kind of the special types of series that we know quite a bit about in terms of convergence or divergence. This next series in part B, it looks like it has a geometric part, but it is not geometric. Okay, so it's not geometric, so we can't actually use that. Instead, let's go ahead and use the ratio test. So looking at the n plus first term compared to the nth term in the sequence, not the series, but the sequence, we have 3 to the n plus 1 all over n plus 1 times 2 to the n plus 1. And just like before, I'm going to multiply a sub n plus 1 by 1 over a sub n, so the reciprocal of the nth sequence term. All right, now everything inside is positive, so those absolute value bars are redundant, so we can drop those, and I'm going to kind of commute a couple of these factors around so that we can see each of the pieces next to its friend. So 3 to the n plus 1 over 3 to the n. Then we have n and 2 to the n. And then in the denominator, we've got n plus 1 times 2 to the n plus 1. So the 3 to the n plus 1 and the 3 to the n, those will cancel. Okay, so this guy cancels that n power, that nth power of 3, so you'll just be left with 3. The 2 to the n plus 1 in the denominator and the 2 to the n in the numerator, they cancel, leaving just a 2 in the denominator. And please do not do bad algebra. The n and the n and the n plus 1 do not cancel. They don't cancel. Okay, so we are left with 3n all over 2 times n plus 1. And as we take the limit of this ratio that we just reduced, nope, copy, paste. Okay, so the ratio that we just reduced to 3n over 2 times the quantity n plus 1, that limit, and you can do this a variety of ways. You could use L'Hopital's rule if you like. This is 3/2. Now, by the ratio test, well, not by the ratio test, but what we care about is if this is bigger than or less than 1. It is bigger than 1, so by part B of the ratio test, you know that this series diverges, okay? As you go down the line, the next term in the series in magnitude is larger than the previous term. So this thing is not whittling down to some finite value. It's going to get larger and larger. All right, so the series diverges. Last but not least, oh, by the way, I meant to kind of be kind here. So this exercise is like number 7. This is, I guess, if you're in Dr. Ismert's. Hi, that's me. If you're in my section, that's your number 7 on the 11.6 homework. Also, we did something similar to problem 6 right here. This is sort of like number 6 on the 11.6 homework. Regardless of whose class you're in, those 2 problems are probably on your WebAssign, even if those aren't the actual numbers that they are. Okay, last problem. Let's do this. So again, this is an alternating series, just like in part A. This is alternating, and that's just good to remark. Now we're going to use the ratio test, but you'll see. I'm not going to tell you. Let's just do it. Okay, so the ratio of the n plus first term and the nth term. Again, I'm going to take the absolute value of a sub n plus 1, and I'm going to multiply that by 1 over a sub n, which would be the reciprocal of a sub n. Now, because we have absolute values, those negative 1s to a power, regardless of what n is, they just become 1. And natural log is always, as long as the input to the natural log is bigger than 1, it's a positive number. And of course, we're multiplying something larger than 1 by 9, so we're definitely positive there. And we're definitely positive there. Good. Okay, so that is the ratio of the n plus first term to the nth term. And now what we want to do is check and see what this ratio ends up doing as we drift off towards infinity. So we're computing the limit as n goes to infinity of this expression that we got by reducing the ratio. Okay. Well, what happens here? So as n goes to infinity, natural log of 9n, that's going to go to infinity as well. Natural log increases, and it increases without bound. Similarly then, the denominator goes towards infinity. Now, it's true that the values for n that we're looking at are what are called discrete. We're not plugging in all real numbers continuously. We're plugging in 1, 2, 3, 4, and 5. But if, let me say this, if the limit as x goes to infinity of natural log of 9x over natural log of 9 times x plus 1, if that exists, then this simpler limit exists and equals the same. Okay, so let's go ahead and compute this guy. That still goes to infinity and to infinity. Hey, what can you do? You can do L'Hopital's rule. So by L'Hopital's rule, that limit can be changed to look at the derivative of the numerator. Well, the numerator's derivative is 1 over 9x, chain rule, multiply by 9. The denominator's derivative is 1 over 9 times x plus 1, chain rule, times 9. And what we end up with when we do some cancellation and some flipping of that denominator fraction to the numerator is we end up with the limit as x goes to infinity of x plus 1 over x. And again, this goes to infinity over infinity. We also are pretty familiar with the limits of rational functions, so whatever you choose to do here, you could say by L'Hopital's rule or by end behavior, this goes to 1, okay? Which means, since that goes to 1, this limit goes to 1 as well. Now, what happens, let me go up here. What happens if the limit of your ratio of your sequence terms goes to 1? Turns out if it's equal to 1, you cannot apply the ratio test. It doesn't tell you anything. If it's 1, there are series that converge or diverge. So basically, this tool does not work for this series, which is okay because we already identified that this is an alternating series. because it's alternating, we can use the alternating series test instead. So let's do that. So the first thing we have to check is that our base terms of the alternating series are decreasing. Okay, so that's a sub n plus 1. Sorry, not a sub n like we were doing here, but our base terms in terms of an alternating series. So this term is smaller than natural log of 9n. Why is that? That's because natural log is an increasing function, which means that if you plug in something big, it will be, the output is larger than if you plug in something smaller. Okay, good. So that checks out. And then the second component is, what is the limit as n goes to infinity of natural log of 9n? Okay, so here we want to know what's happening to the denominator. Because natural log of an input, as that input goes towards infinity, is increasing without bound, this is 1 over something that becomes infinitely large. So in fact, this does go to 0. So I'll put a check mark there. That means that this series converges by the alternating series test, but the ratio test couldn't give us an answer. So that's just something to keep in mind. Different tests can be utilized depending on the type of series. If you have a geometric series, you can use the geometric series test. You can't use an alternating series test unless that series is alternating. And similarly, if you have an alternating series, you can use the alternating series test, but you cannot use a geometric series test on an alternating series unless the alternating series is geometric as well. Some series are not checked by the ratio test. And so part C here is just an example of a test that fails, and you have to go back to your first step and say, what other tools do I have at my disposal? All right, guys, good job. This was a long video. This is hard stuff. If you have any questions or need clarification, make sure that you look at the neatly written solutions. They're not these that I've written here. They are nicely written and they should be on your Canvas files, or just ask myself or Dr. Hamidi. Okay, bye guys.